Hello, everyone. My name is Usman. I formally welcome you to the Permafrost Network Seminar Series. And today, Hannah would be presenting on development and demonstration of statistical ranking framework for ground temperature models tailored towards permafrost environments. Hannah is completing her master's in geography with the specialization in data science working under the supervision of Dr. Stefan Gruber at Carleton University. Her thesis was on the development and demonstration of statistical ranking framework tailored towards permafrost environments. She currently works at Environment and Climate Change Canada as a data scientist. Hannah completed both a BSc in Computer Sciences and a BSc in Climate and Environmental Sciences with honors concurrently at St. Francis Xavier University. So over to you, Hannah, for the presentation.
Thank you, Usman. My name's Hannah. Thanks for coming in. And yeah, we'll do some questions at the end. So if you're on this call, you probably know a bit about permafrost and maybe a bit also about different permafrost adaptation practices and how they can be supported by modeling. And I'd like to elaborate on this a bit. So modeling, I like to think of as inherently a heuristic activity. So it's relying on using simplifications of the natural world that maybe aren't guaranteed to be perfect, but are useful for learning or establishing estimates of otherwise an unsolvable problem. So for example, making predictions of severity, timing, or location of permafrost change, be it present or in the future. And within this context, specifically at the local scale, so characterizing things like ground ice, the active layer, carbon content in the ground, and ground temperatures where we don't have direct observations available to us. However, it's important to acknowledge that there is significant variation in the predictions that are made by different models. And so if we want to ensure their reliability and their usefulness in climate change adaptation and research, we have to be able to establish trust. So, reliability and consistency in the predictions that are being made. Unfortunately, there are some obstacles in the way of evaluating models. So I'm going to talk about these today. And these issues include things like a lack of consensus on one specific approach to model evaluation, so lack of statistical consensus, the intangible nature of the values that we use that can really prohibit a clear interpretation of model performance, both the limited spatial coverage and incompleteness of measurements that we use for model validation, and finally, the unfortunate discrepancy between what we're able to observe and what permafrost variables we're really interested in. So the aim of my project was to improve the value of permafrost modeling outputs, and doing this through providing an accessible tool, a software tool that would rigorously test model output. The ranking framework was designed to offset some of these challenges. So to demonstrate and test the software, this ranking framework, I used ground surface temperature data as a case study. And this was in part because of the large network of existing sites that my research group has access to throughout the Northwest Territories. So these maps are showing 3 different clusters of GST sites that I use to evaluate model simulations. So we have sites around the Yellowknife municipality that is shown in blue, as well as 2 other clusters northeast of Yellowknife. So KDI that's shown here in yellow, and Lac de Gras in red. So GST is it's an interesting variable. It's the temperature recorded just below the ground surface. And ground surface temperature is an interesting variable because it can tell you a lot about what's going on below the ground surface. And it's also relatively inexpensive to measure, especially if you compare it to something, putting in a borehole. So these mini loggers on the upper left-hand corner, that are used to record temperatures, they're quite small, comparable to something like a hobo logger, if you've ever seen one of those, or the same size as a tube of mascara. And you just kind of plunk that in the ground 10 centimeters below, and it'll be able to record temperatures. So here are some photos from the fieldwork from 2022 with Olivia and Galina, 2 other graduate students from Stefan's lab. And while these photos don't really add scientific value to the presentation, I just thought they would be lovely to show for context of some of the terrain that we're working in. These photos were taken around Lac de Gras, and we were there in late August, early September in 2022, and it was really stunning. There were cranberries that were starting to come in, so lots of snacking in addition to science. But more importantly, this is the photo that I was looking for when I found the earlier ones. So this is what a typical site would look like within one of these clusters. And so though they range in size, each plot is roughly 10 meters by 10 meters, and they contain anywhere between 3 to 4 ground surface temperature mini loggers. And you can see where they are on this plot. They're marked by these kind of red-orange flags. So a subset of these sites across these clusters also contain boreholes. And you can see here, there's one, the borehole infrastructure set up with that white kind of tube cap. So this in general was the setup of a location for which I would be producing multiple simulations for and then ultimately evaluating. And so although the bulk of my thesis is about the ways that we evaluate simulations, I'm just going to spend a few slides walking through how those simulations were actually produced for so many locations for evaluation in this case study for ground surface temperature. So in order to tailor geotop to each location of interest, so geotop was the model that I used for my case study, you can use parameters, right? So parameters are the empirical, or so the numerical way that we're describing a location. So on the right, we see a rough drawing, a doodle, so to speak, of what components of the natural system were used here to generate estimates of ground temperatures. And this is obviously a simplification, but for the purposes of this study, this included things like vegetation, snow collection, shading from surrounding topography, and then also the drainage, so the terrain wetness at a location, in addition to subsurface ground materials. So one component of the framework really examined this idea of grouping together sites that could be described as the same terrain type. And the reason we do this is so that when we're evaluating our model, we can adequately weight each terrain equally and avoid skewing model evaluation towards terrain that you may have more data for. So once each location was assigned descriptions of things like drainage, vegetation, and snow correction, soil material, what I did was I then grouped them together with other sites that shared those same surface characteristics. So the table on the left here is showing these categorical parameters, how they were assigned to each terrain type. So these terrain types included things like peatland, coarse and fine hilltop sites, we have snowdrift sites, and horizontal rock sites. And on the right, you can see a nested pie chart, and that shows the distribution of data I had not only for each site that was ultimately included in the case study, but also for each terrain type. So although there was some variation, I actually ended up with a relatively even distribution of data across the terrain groupings that were selected. And just for reference, each site here, each kind of section of this pie is 3 or 4 mini loggers at each location. And so the 3 or 4 mini loggers at each of these sites are then averaged to produce one temperature time series that's used as my observational data. So to produce simulations for evaluation at each of these sites, I used 3 different driving data sets. You can see them on the left here. And I did that in combination with the model geotop. And then I evaluated their individual outputs in addition to an ensemble mean. So to break this down, on the left, you can see there's 3 different reanalysis data products. So we have the Japanese reanalysis, GRA55, MERA2, produced by NASA, as well as the ERA5 data. And so each of these data sets are these very coarse, gridded, 3-dimensional products that are downscaled to point locations. So they're kind of transformed into a meteorological driving data that I can use. And that's done through a software called GlobSim that I won't speak on too much today. But these are then passed to geotop. And so as they're kind of put into geotop as the driving data, they're also parameterized using the same set of geotop parameters. So in this case, as I had 5 different parameter sets, one for each of those terrain types that evaluated and shown on the previous page. And so as the output of geotop is a combination of this driving data set, this parameter set, and this model, I have 3 different sets of simulations that I'm able to evaluate as each of their own kind of distinct model. And then additionally, I took their ensemble mean. So I had a whack ton of temperature simulations for these locations. And given the timeline of a master's thesis, it just made a lot more sense to learn the ins and outs of one modeling software, in this case, geotop, and use the different reanalysis data sets as a way to sort of emulate different models for evaluation, as opposed to actually learning, different modeling software. So the simulated output from each model is then fed into our ranking framework. And this ranking framework, so this is kind of the crux of the thesis, it was initially named by another student. So it was called Acomatic because it automates the application of a bunch of accordance measures, accordance, Acomatic. I thought it was fun. So I did not name it myself, more adapted it to kind of suit this thesis and this case study. But this schematic shows how this software works. So first we have 4 models and a set of observations that are being fed into this software. What Acumatic does is the data is then sorted into their respective terrain types and then are also partitioned by month. And I'll speak more to why it's done this way in future slides. But in the end, given that I had, for my case study, 5 terrain types and there are 12 months of the year, there were 60 kind of terrain month groups. So for instance, I had one data subset called peatland January, which could contain up to like 30 different month-long time series data sets from multiple sites within that terrain group. And another that might have been snowdrift May and so on and so forth. So each of these month terrain groups were then bootstrapped, so sampled with replacement. And that was to generate a mean and spread of model performance for that grouping. And so if this is unclear, don't worry, we're going to come back into it. I'm going to go through kind of each of these decisions a bit painstakingly, but I thought this was a good visualization to start off with. But ultimately, Acumatic was designed to really address these barriers that I identified earlier. So what are these things that are limiting our ability to test models in permafrost simulation? So I'm going to speak to each of these and how we think that Acumatic as a software kind of addresses some of these. And I really hope you like these slide transitions. They were fancier than I was expecting. So the first of these challenges being the lack of statistical consensus on which metrics we should use to summarize model evaluation. And what that means is we end up with a bunch of different numbers to summarize performance in the literature and no clear way to compare them. So if there was one main takeaway from my reading on summary statistics, it's that you really have to tailor your statistics, the way you're evaluating your model, to a predicted variable. So what variable of interest you're looking at. And so for that reason, the Acumatic software was written so that any summary measure you want is readily available or easily integrated. But today I'll speak primarily to 3 that were selected for ground surface temperature and why. So stats measure all kinds of different things. And the first group I'm going to speak to is this sort of dimension statistic, that the group that tries to gauge average error. So here we have the example of a root mean square error, which I'm sure many people are familiar with, and the mean absolute error. So these are 2 widely used statistics that kind of describe average error over a study period. And root mean square error, despite its popularity, is known to be highly sensitive to large and low frequency outliers. So here we have a pretty extreme example of 2 models. So one we have shown in orange that's so closely aligned with our black observational data, it's so hard to see. And again, sorry, this is all dummy data to hammer down a point. Just thought I'd make that clear. And even though the total error of this blue model is twice as much as model 1 that's shown in orange, a root mean square error is ranking this blue model as better, and that's because it's able to capture these low frequency but large outliers. And this is an example of how root mean square error and similar metrics to it that kind of scale the error values, despite popularity, are very sensitive to outlying error, which may not always be what you're most interested in. So while this is, again, a subjective decision being made for this framework, if our aim is to minimize total error over the observed time period, a mean absolute error will serve as a better indicator of that. Second, I want to talk to you about bias or mean bias error. So here we have an example of an orange and a blue model that seem to perform identically, right? So that orange line that's above our observed data and the blue that sits below it. And they have the same value, a mean absolute error of 5. And it's only when we examine model bias that we can tell really how vastly different they are, one being significantly warmer than our observed data and the other one much cooler. In contrast, though, without the addition of an absolute error, without the addition of an average error-based statistic, we actually might look at model 3 here. So it's this janky kind of stepwise red model as the perfect model. And that's because we have all of this positive and negative error that cancel each other out. So it ends up with a mean bias error of 0. So this kind of shows how these 2 metrics really complement each other. And I like to use this joke, and I apologize. I think there's several people on the call who have heard me stumble through it before, but it's about, a statistician can have their head in the oven and their feet on ice and say that on average, they feel perfectly fine, right? So no summary metric is perfect in isolation. And for these reasons, we can see why multiple stats should be used to evaluate model performance together. And lastly, I just want to quickly point out a well-known problem with correlation. So Pearson's correlation coefficient. So scientists love using correlation to evaluate models. And to quote Wilmot, he uses this expression a lot, which I really like, that says, something has historical inertia in science. And Pearson's coefficient definitely has a bit of that. But there are two problems with this measure, at least in this application. The first being that R can rapidly approach 1 when a time series has seasonal trends or any kind of temporal structure. And the second is that R is a measure of signal response timing, not a measure of error magnitude. And so here's an example on the right where we see the timing of this just terrible orange model, but it's perfectly aligned with our black observations as far as when, temperature is increasing or decreasing, and it scores perfectly, better than the much more closely aligned red model here, right? So if you're focusing on reducing model error, correlation might not necessarily be your friend. Another metric that was considered was Wilmot's refined index of agreement, which is perhaps lesser known. But what we found was that it really fell apart when evaluating values close to 0. So for instance, you can see that the highest ranked model by Wilmot's refined index of agreement is this yellow model. And the blue model, which again aligns so closely with our observations, it's actually quite challenging to see. It's scored as a 0.55, where perfect performance for a Wilmot's index is 1. So ultimately, we selected Pearson's coefficient as a third statistic, but with a bit of a caveat in mind. So one thing that I speak to a lot in my thesis and less for this presentation is that the model ranking framework is really focused on establishing relative performance, and it's not about establishing or asserting model validity. And so while Pearson's coefficient might be inflating model performance, we really only care about what it tells us with respect to the other models. So it tells us which model is the best correlated and not necessarily whether it's objectively correlated at all, if that makes sense. So in summary, for this application of evaluating ground surface temperatures, we selected mean absolute error bias and Pearson's coefficient. The second issue that we kind of looked at was the fact that statistical values are intangible in realities. You can't hold a Pearson's coefficient in your hand. It doesn't exist. It lacks units and dimensions. Often a lot of these statistical values are mathematically unrelated. And so to improve our understanding of relative performance between models that are being evaluated, the framework did focus on ranking. So how do we break down these numerical values into just ranks? And so on the right, we see this distribution of ranks. So it's not necessarily this model was first, but how often did it place first? And this is one of the outputs of the ranking framework. So it communicates the likelihood, so the confidence assigned to each model having ranked first, second, third, and fourth across all observations and testing conditions. So this plot on the right is showing the aggregate ranking distributions across all data subsets that were evaluated. So that being snowdrift sites in May or peatland sites in January. And what I mean by that is if we think back to the process of how the model is subset by terrain and month and then evaluated across different statistics, we're essentially producing a wide distribution of performance for each terrain month pairing evaluated under our Pearson coefficient and mean absolute error. And then when these values are aggregated, we can see the likelihood of each model having ranked first through fourth. So just to really hammer it down, for example, we see that model 1 on the top ranked first in 27% of our bootstrap samples. And in contrast, we have something like model 3, which ranked last like 58% of the time, right? Not doing so hot. And so the last issue that we really addressed was, last two issues, was in the ranking framework was the very limited nature of observational data. So to ensure an unbiased evaluation of model results and to avoid introducing seasonal biases, complete years of data are often favored during an evaluation process. So this is often done to avoid having, too much of January, influencing your model results and whatnot, if that makes sense. But this approach leads to a significant amount of data being excluded from the valuation of the model. And this is shown as kind of the leading and trailing bits in red on this plot that would have to be removed. And in order to address this issue, the ranking software employed a bootstrap procedure. So first, it divides that model and observed time series into these month-long segments. and then randomly samples from the segmented data for each month of the year, which means that leading and trailing months can be used without influencing results. And so in the end, you can get this nice picture of the distribution of model performance for each month of interest that then is aggregated into those ranking distributions that I talked about earlier. So the next challenge we wanted to address within the ranking framework was the unequal representation of terrain types or spatial distribution of observational data. So ground temperatures, they're primarily controlled by climate, but the microtopography or the local surface features are really what controls the extent to which climate signals either attenuate with depth or even manage to reach the surface. So this plot on the right shows a very high degree of spatial variation in ground surface temperature. This is just a small subset of observational data that I use to show how differently terrains respond to similar driving climates, just given differences in drainage or vegetation, shading, and snow. And the problem here is that Canadian tundra is incredibly heterogeneous. So much of this is underrepresented in observational data sets. It's a lot of this expansive northern landscape that we can't sample uniformly. So identify and subsetted model performance by terrain type. That means we can better understand how our model is performing in different environments and remain transparent about model limitations. So the last portion of my project looked into how our model ranking framework extended to other variables. So we have this issue where the variables that we have lots of observations for, such as ground surface temperatures, are not necessarily what we're interested in when it comes to future permafrost change, things like thickening of the active layer or ground ice content or changes in these. So using the ranking software, I measured the extent to which model performance at the surface, so evaluating the ground surface temperature simulation outputs, differed from performance at deeper depths. So in this case, 50 centimeter depth. So on the right, we see a comparison of ranking distributions at the surface and at depth for each statistic and terrain testing condition. And so here, while I did find that ranking distributions were similar at both depths, there are limitations to answering this question with a given data set. So as you can see, there was a correlation, but the difference in performance observed at depth versus 50 centimeters was marginal. And this makes it difficult to confidently attribute minute variations in performance to either particular statistic or terrain. So my main takeaways, so to address the lack of statistical consensus, what I found was that stats really needed to be tailored to each individual modeling application. There was no one shoe fits all. An example of this that we saw here was, selecting Pearson's coefficient over Wilmot's refined index, given the large proportion of our data set that hovered around 0 degrees Celsius. And though this may not apply to many variables of interest, I will reinforce the idea that using a range of statistical measures as opposed to one is really necessary to fully understand model behavior and is helpful for identifying sources of systemic error in simulations. Second, to ease the interpretation of statistical values, we elected to reduce stat values into rankings. So for each month terrain pair that was bootstrapped, we recorded not only the statistical performance of each model, but also their relative rankings. And this meant that we could produce ranking distributions that were communicated with confidence relative performance over our study time. The caveat of this being that ranks obviously can't express magnitude of error or magnitude of performance, only the frequency with which one model performed better than the next. To address the limited spatial coverage of observations in permafrost environments, we decided to ensure equal weighting across all of our terrain types. I will say that by the way in which we went about parameterizing our terrain type groupings, using these categorical parameterizations for terrain groups may have impacted simulation quality because there was variation within how well a site kind of met their prescribed parameterizations. For incomplete observations, we did look at subsetting data by month prior to bootstrapping, and that allowed for additional data to be factored into analysis. So I don't have the number in front of me, but it's something to the order of like 20% increase in the amount of data that could then be factored into analysis, just in the addition of these trailing and leading months that otherwise would have been excluded. And then lastly, looking at the way that observations could be not always the same as the variables that we find most interesting. So looking at, well, is the output of this model ranking framework, if we're really confident how a model is performing at the surface, will that extend to deeper depths at 50 centimeters? And while I was able to kind of ascertain, okay, yeah, there is some correlation, I would say that this requires more data and deeper temperatures or other much more different variables of interest to be certain to answer this question. Thank you very much for listening. That's the extent of what I have to share today. So thanks so much and I'll take any questions. Igor, go ahead, jump on in.
Thank you very much for a very interesting presentation. So my question is regarding the application of your work in a geotechnical field, like foundation assessment or infrastructure assessment, or just geotechnical investigations. So is it possible to amalgamate all these models in, let's say, several groups of taxons regarding not months? We can just amalgamate by season, freezing season and thawing season, but we can actually add a location in terms of, what the permafrost zone or latitude, longitude, or just, because the temperature is changing because of how far we go into the north. And so if we can get the stable groups, we can say that these groups actually very different from each other, and we have to develop the specific approach, for example, to geotechnical investigation to first group, second group, third group. So is it possible to create the taxons, let's say, environmental conditions or geochronological condition taxons based on these models amalgamation?
Thank you for your question, Igor. So I think there's a two-parter in there. So for one, as far as other variables that it could be applied to, I will say it's very much designed for any time series variable. That's definitely what it's best suited to. So just when you're saying geotechnical, whatever data set you want or whatever variable, so long as it's a time series variable, this model is readily applied. As far as subsetting by other conditions, I think you mentioned a temporal one. So being able to use the freezing and thawing season, very doable. That's already kind of part of the software. So there's kind of a parameter set up for the model. And in mine, I stipulate I want it to be run by the 12 months of the year. That's how I want my data to be subset. And that was kind of the product of early discussions on saying, well, what's a season? We're talking about freezing and thawing seasons. We talked about, the very westernized 4 seasons of the year. That there was kind of a lot of discrepancy, or there's different ideas as to which. So breaking it down into 12 months made sense for this application. But by all means, you could do it by any temporal structure you wanted to apply is feasible. As far as I think you mentioned, kind of separating it by permafrost zones and whatnot, it's not readily available the way I've written the software now, but by no means would that be difficult to accomplish, because right now you can do it by depth, you can do it by time, by statistic, by terrain type. Like adding another dimension to that increases the complexity or the runtime, the CPU to runtime of it for sure, but it's not by any means infeasible to add that in. I hope that answered your question. Any follow-ups at all?
Yeah, I have idea. Thank you. Thank you very much. Thank you.
Yeah, no problem. Thank you for your question.
Can I have another question?
Yeah, sure.
I have a question about that amplitude. You just shows us different models that actually can have a log, shifted to the right, to the left, and different amplitudes, which is probably it doesn't fit. But if you find the perfect, actually the model which is according to your coefficients, different coefficients actually can give us real results and can give us, let's say, calculate the estimation of a daily average temperature. Is it possible to play with this and to predict the daily temperature and amplitude of the change of the daily temperature, let's say for the night and day? So exactly, did you have any estimation of a amplitude change of the models?
I think
it's not clear because it's two topics together. The first topic
yeah.
is that I'm trying to actually observe how the temperature amplitude is changing during the penetration into the soil with all these factors, latent heat and everything. So your model actually involved maybe the ground temperature, right? So in this ground temperature, with the ground temperature freezing and thawing, there is a latent heat. And if there is no latent heat, the amplitude would change according to the theory of distribution of this variation into the media. From this point of view, is your model can be useful to actually to define this amplitudes of change of amplitudes of daily average temperatures in the soil?
Okay, I think I understand your question. I'm going to answer it, but please cut in if I misunderstood. So the way that Geotop works, the simulator that was being used, is it does change the ground temperatures based on whether it's frozen or unfrozen. So the simulation, I show results for 50 centimeters depth, but it actually goes, much further into the ground. And given, in the winter season when that ground is frozen and I'm still driving with surface meteorological data, the thermal properties of that ground is frozen and thus changed, if that makes sense, versus when it thawed. So it does account for water in the soil, if that makes sense. Does that answer your question?
Yes.
Yeah, okay. Yeah, no, so Geotop does function that way.
Okay.
Aside from my evaluation model, but yes, that is how the simulator works. Yeah. Okay. Thank you.
I think your answer was great. So Igor, you kind of said according to the theory of how the amplitudes are dampened. So I mean, that theory, there's a simple analytical expression that works without latent heat. But with latent heat, it needs to be solved numerically. And this is one of the models that does that reasonably well. And so you'll get a realistic influence of snow on the amplitudes of surface covers if you prescribe them, such as organics, and then of the distribution of latent heat according to the freezing characteristic curves with whatever stratigraphy you describe.
Okay, thank you, Stefan.
Well, thank you for your questions, Igor. Any other members of the audience who would like to ask a question?
Hannah, this is Joe. I like your talk a lot, and I don't have questions because I've seen this and talked to you about it before. Thanks, though.
No, thanks, Joe, for your comment. I appreciate it. Cool. Well, thank you, everyone. I really appreciate your attention and allowing me to speak of my work. It's always nice to talk about this to an audience. So thanks.